Previously on The Bald Engineer.
Alright, I'm gonna do it the way Geek said, because he said just put it on the board. You go plop, plop, plop. Ooh. No! Right here. Yeah, so now I'm going to open it up to help cool. Ow. really? You can't put caps into the resistor box. That's just ridiculous. Oh, right. Ooh, I don't have that part. Ha, 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 ha. Okie dokie, now we can get started. Hello everyone, welcome to the stream. I'm James, you're you, and we're going to do some fun electronic stuff. How's everyone doing? Let me double check. Okay, so I think tonight's going to be interesting because this is the right one. That looks like the right one. That looks like one I've never used before. Because we're going to try something that I've never tried before. Okay, so here's the deal. Oh, that is not... that is not what I want it to do. Because desktop is the other desktop. Okay, let's try that again. All right, so over on here, we have, so this is the schematic we worked on last week. This is a Raspberry Pi version of what I call a state mode logic analyzer. State mode meaning the device under test drives the sampling clock. It's not an asynchronous timer like with most logic analyzers, especially Pi Pico based logic analyzers. Now, one of the things you need in order for this to work correctly is a way to skew the clock away from the data, because generally in a system, the clock changes with the data and then it gets latched at some other point. We need to make sure that our clock is skewed away from when the data is transitioning so that we can get stable captures. And one of the ways that I thought to do this is I found this little circuit from Linear, which is now Analog Devices, I think, which is literally just a clock skew. It's a digital delay. And so based on the voltage on pin 3 and the voltage on pin 4, it will set a certain delay. And then there's also, I think you can actually divide that delay. So that's why there's like a divide and a set, if I remember how this works correctly. So here's what we're going to do. On my old boards, now, in order to do that, what I wired up was a digital to analog converter for the div pin and a digital potentiometer for the set pin. And so the idea is, which in retrospect, I probably could have just done a DAC on that as well, since I think it's just creating a voltage divide. Anyway, well, oh, excuse me, sorry. But that's not what I'm doing. So anyway, what we need to do is first we're going to see if this chip is even functioning, which I think that it should be. And then we're going to try and talk to these two chips with CircuitPython. The DAC is going to be easy because there's already libraries for it. The pot is not as simple, so we'll see how far we get with that. Audio is broken. Okay. Let me see if I can hear it on the, if I can catch it. It's going to be easy because there's already libraries for it. The pot is not I don't know what's wrong with the audio.
It's broken.
I ran a test before I started, and it was fine. Oh, I wonder if it's something to... Okay, I wonder if it's something that's only going to the Twitch stream, because YouTube says it's okay. That would help explain why I can't figure out what the problem is. Yeah, sorry. We're gonna just have to deal with it because I don't know how to fix it today. I'm gonna have to run some test streams because there's nothing I can do. So anyway, okay. Sorry. Looking at the overhead. So here's what we're gonna do. So these are the revision 1s of the state mode logic analyzer that I was working on, and so first thing we're going to see is whether I can get CircuitPython to program onto either of these, and then we're going to see if one of them will do the if we can actually talk to one of them. So what do you use as a splitter? I'm using some plugin for OBS. I think it's literally just called... Oh, I don't even know what it's called. I think it's just called multiple output. It worked. It worked before, so I don't know what's changed. Yeah. It's also possible that I didn't listen to a long enough clip, but I talked for a while because I was trying to make sure that anyway, I don't know how to fix it right now. So first thing we're going to do is see if we can get this going to bootloader mode. Boot, reset, release. And then I'm not going to show my desktop yet. I want to see... One of these boards should connect. I think the other one doesn't. Okay. Well, let me think. Have I rebooted since last week? Yeah, I did. Okay. Oh, that's why. I'm not plugged into a... So I'm trying to get these... So these are RP2040s. I'm trying to get them into the bootloader. That one's not going. Let's try this one. Oh, okay. That one's not working either. Yeah, actually, this one's not. The reset button's not working. If I can just get it to go into the bootloader once. Nope. Okay, so the buttons aren't working on that one. Let's see if we can get this one. Nope. Sweet. All right. Yeah, I remember now. I was having trouble with these push buttons. I think I melted them when I was soldering the boards. Okay. Next, we're going to try... Well, let me think. So if that's not going to work, then... But it's CircuitPython, so... Does CircuitPython come in a binary, or is it only in a UF2? looks like just the UF2s. Well, shoot. So let's see. Okay. The problem is the problem with it being anything hardware related is that I don't have an issue with anything other than OBS. So I don't know. There's. Oh wait, you're talking about. Sorry. Or yeah, I don't know if you're talking about the audio or the board. It doesn't matter either way. Okay, so shoot. Okay, so what we're going to do is I'm going to desolder. Well, no. I want to scan. So let's do this. Let's grab one of these. So I use this one. Okay, let's try this. Oh, wait a minute. Yeah, okay, there it is. Okay, so let's get device manager so I can figure out which serial port so we can go back to how do you hide? Yeah, at this point, that's probably fine. Okay. Okay, so let's see. This is going to be on COM port 4, which we'll just do serial COM 4. Baud doesn't matter. Go Control D, Control C. Okay, so then we get into CircuitPython. Yeah. So now what I need is I need the I2C scan code. I2C scan CircuitPython. Ah, come on. Why are they paying for a search term that is super easy to to work? Like it's very, very likely to work. All right, so do this as old code, and then I'm going to do file new, folder, new text. I'll call this code.py. So basically, I want to see if I can scan the boards that we have, even though there's RP2040s on them. And if so, then we're just going to move forward. So all of that. So I should be able to just reload this now. No that I2C bus found, which is actually that it might actually be okay. That generally means I don't like this. I don't like this at all. I got this to work with the S3 before, and I don't remember what I did. So let's try. Let me go find see if I have a copy of the old code. Because that would have been BaldSense that I was using this originally. All right, I'm going to look in one more thing. I guess I'll go to this for the moment. What is this? Oh, I know what happened. Hey, Del Morte, good to see you. It's been a long time. Hey, Boris. Welcome to the stream. I came in here to look for I squared C. So what ends up happening, what I think ends up happening, I thought I had wrote a really good okay, I see what they did. Okay, I see what we should have done is just should have just done this. So I squared C in CircuitPython fails if it doesn't find any really whatever. Yeah. So it's okay. So it can actually be okay that it's complaining because CircuitPython will complain if there's no valid I squared C devices. And right now I don't have anything connected, so there should be no valid I squared C devices. Which actually threw me off for a while. So thanks. So which pins are I squared C on here? Those two, and then ground is 1, 2, 3, 4 from the top. So that should be ground. Nope, totally did that wrong. 1, 2, 3. So that should be ground, and then over here is SDA and SCL. Okay. So then we're gonna grab, I did not grab, did I? I did not. Grab a couple of these. And then I want. Are you kidding me? Are you kidding me? I don't know where my mini hooks are. What else do I have? Where is my bus pirate? Because that has many hooks in it. I just remember where I put that. Which I probably should get this out anyway because we may want to use it. Yeah, I was really hoping we could have just used the RP2040s on the boards, but I thought I had working versions with the delay circuit, but it looks like I don't. So that's a bummer. El Bumro. Okay. Put these over here. Alright, and then we'll just connect this to here. Do I have a good ground somewhere? I think that's what this one is. And then SDA is over there. Man, these easy hooks mean business. They got like a really big, thick pin molding. Oh, and then it came off as soon as I touched it. Okay. But in fairness, these test points are terrible for mini grabbers. They're just way, way too big. They're great for scope probes, though. Do one of these. There. Okay. And then this is SCL. All right. Let's plug that into here. Okay. Let's see how that works out. All right. Survey says, okay, so we'll rerun the code now. Of course, that's not going to work, is it? Yeah. Yep. Got to power the board, James. Oh, yeah. We're just going to power the whole board, see what happens. I actually think I might have made it so that I could power up only this part of the board. But we're going to try doing the whole thing. So need another header. Okay. Nope, not that. Where is 5 volts? It's right here. Okay, remember, don't change connections while you're powered. It's a terrible idea, so don't do it. Whatever you do, don't do what I'm doing right now. And this we're going to plug into here. Oh my God, are you kidding me? Everything came undone. Oh, that's classic. That is classic. This one literally, did it just break? Okay. All right. Plan B. Do I want to solder headers to this board or not? Let me think about that for just a minute. Because we'd get SCL and SDA plus a ground, and then I have a spot where I can do a 5 volt, but then we're committed to that board. Oh, okay. Yeah, I guess we'll do that. So what I gotta do is let's close this. Gotta go open project. Logic Analyzer KeyCAD 2040. Okay, so it's these two, and then just a couple of these. So that'll be power. That'll be clock, or the, and they'll connect down there. Then I wanted to double check, what are these powered off of? Just the 3.3 volt, but so is the RP2040. So I should be able to use this 5-volt pin though, because the idea was you connect, the idea I wanted to take this header, this jumper off so I could go directly into 5-volt. Yeah. Okay, so we just need to add like a couple of pins over here, and then I can get onto all of the signals. In fact, how do I want to do this then? I have a breadboard over here because that would make this super easy. No. Let me think. Where did I have these headers? They were in the Cerberus box. Yeah, I'll just grab. We just need a handful of pins, and then we'll be in good shape. Yeah, something in here must have a usable thing. And then a breadboard, got one right there. All right, so here's what we'll do. We'll do this, and then this will be a heck of a lot more reliable. Because hopefully we can get this on the first board and not have to try to figure out a couple of boards. Do I have like a really small one? That's a little too, let's go with the 6. All right. Okay, so now, yeah, I don't care. Let's do this. Oh, not this one. I want it, the breadboard. This one should be off. I didn't even realize that iron was powered. And then I'm going to plug into like right here. So then I can just do, oh, come on. Maybe I can do one of these. Why are you being a pain? What the heck? What in the heck? All right, come on. Nope, it has to be down here, and that has to be there. Okay. Okay, so because I want these two signals. These are the most critical two. Why can't I get them? All right, well, that doesn't really matter. So now we will dab, dab, dab. Going to solder to here. I'm going to solder to here. And then we'll do this one, and this one, and this one. I really don't care how these look. Okay. I'm going to go for the hope for the best. That's all we got to do. All right, shut those off. These should be cool enough to pull. All right, so now I should be able to take this guy without these. Nice. Fell apart. These are the ones that came in the Bus Pirate. At first I thought they were really good quality. I'm starting to think different now. Okay. So then I want to connect. We don't need to connect power, but we will need to connect ground. So that will be basically, oh, I did this upside down, didn't I? I did. Okay, so that's going to be here. And then SDA is on the outside, so that should be easy. We can connect this to SDA. And then we can connect, I'll do red, SCL to SCL. Okay. Now we can see if CircuitPython will be more happy. Yeah, because I remember running into this when I first got started with the Feather S3. I was it was giving me these, it kept giving me these errors, and I was like, well, what the heck? All right, let's come over here. No valid I2C found. Well, bummer. Let's double check. Okay, I did it again. I forgot to add power. I even said, oh, I don't need power. Yeah, I need power. What the hell was I thinking? So where's that 5-volt go? Okay. Okay. We'll do that. We'll do that. And then this will plug directly into here. Okay. Let's try this again. Restart session. Oh. Well, there's a reason you can't find COM4. Oh, come on, putty. Okay.
And there was much rejoicing. Yay!
So, these are the two devices we care about, 2C and 60. I don't remember which is which, but that's okay. All right, so we'll close this. I'm going to close this. I'm going to reopen this. And what I was going to do is I was going to actually add once we know which one is which. In fact, if I go back and look at this one, looks like the 8254 is 2C. So that's the DAC. And then the 80, oh, no. Wait a minute. Oh, that's the Digipot. And then 2C is the DAC. Okay. That is good to know. So now, hey, David. Good old DB. How you doing? Good to see you. It is a live stream in 2024. I've actually been doing live streams on and off throughout the year on YouTube. I just restarted doing Twitch recently. Okie dokie. Now, I just made a realization. There are 2 I/O pins on this digital pot that I was using for LEDs because I ran out of I/O pins on the 2040. Did we end up with any extra pins? Oh, we're going to end up with extra pins because I'm going to get rid of the timestamp counter. So I'll be able to get the lights back over here. Okay, cool. You know what I kind of want to do is I kind of want to just do this right now. And worry about that later. Because I don't want to yeah, I guess we could go ahead and delete this now. So between LT and Geek, they have convinced me that we should be able to get timestamps internally and without an external counter. One of the only reasons I had the external counter before is because the original design was going to be that you had two of these boards next to each other to get to 32 signals. And I needed the timestamp counter to keep the two sides in sync as well as to tag the samples. But since everything's in a single chip now, there's no reason for us to have the timestamp counter external. So we're just going to chuck it. Okay. So item number next is, let's see. I guess we should figure out how to get a clock in and out of the board. That might be a good idea. So I think now I realize we're going to have to solder a couple more headers. So I'm going to disconnect that so we can get to the soldering iron. Turn the soldering iron back on. And let's go with, we'll just go with regular headers. Nope, that's a test header. So that's a test header. All right, so clock will be pretty easy. It's right there. Why won't those go in? What is going on? What is wrong with this? Wonder if there's something in the hole. Where'd that breadboard go? I need something I can really push against. Okay, that's garbage. Let's try this one. So if I do this, and then I do this, okay. So that's going to get us the next one that we need. So that'll get us our clock in. And then I got to find a place to get the clock signal, which I think the best place to get that's going to be off this same header. Yeah, we're just going to do a set of pins up here. And then that way we can, because then I'm going to connect the analog discovery to be my clock generator, which could actually probably do it as my power too, but whatever. Okay. Right. So then that way we can control these two chips. Well, this chip and that chip. And then I have access to the DAC signal here. Okay. That should be what we need to make this work the way I want. All right. So then we can go and say, let's connect. This was ground. So that just connect to pretty much any of these. And then SDA is on the outside. And SCL is on the inside. 5 volts is over here. Okay, and then let's get this guy, and we'll go ahead and hook this up now so that it's ready to go when we are. We'll put a ground here, and we'll go ahead and put a ground over here since there's two available. Well, you know what, we'll use one of the grounds closer to the digital. Okay, so we'll put that over here. And then I want the scope input. Actually, that's what I want to do, is connect these two right here. I want to see the waveform on the scope. Come on, what are you doing? All right, and then I can put this ground over here somewhere, just so that we have more grounding to the input. And then I think I want digital 0 to be my clock in. Oh, but then how do I see that on the scope? We'll worry about that in a minute. Okay. Now, let's go ahead and get waveforms, save a thingy. So we're connected, right? So let's do a workspace save as. Man, look at all these golden delicious projects that are in here. That's crazy. All right, I guess I got to do this first. Record to file. I don't want to record to a file. What do you? All right, now we can do a save as projects. This is okay, we'll call this one 10, and this will be clock delay stuff. All right, so the idea was I want it to come in here and I want to do a pattern on bit 0, and I want it to be a clock. Kilohertz sounds fine to me. And I want to run, well, actually we'll just run that, and then I'll run this, and then the scope, oh my, we already have our signal is getting through the, that's a good sign. Huh. So if we change this to 10 kilohertz, yep, okay, that's a really good sign. So basically, oh, I meant to do 1 kilohertz. So basically, Analog Discovery is putting a clock signal in. The clock delay chip is delaying it, maybe, and then it's outputting it. That's all that really matters at the moment. So that's actually a good sign. So now what we can start to do is we're going to start playing around with the two control signals. Let me show the schematic one more time. So this is the clock chip. So it has a clock in and then a clock out. It delays based on the values of div and set. So I have a DAC connected to div and a potentiometer connected, digital potentiometer connected to set. And I can't remember now why I did a digital pot and didn't just connect, why I didn't just do another DAC here. There was a reason, and I can't remember what that reason was. Okay, so we know the address for the DAC, and I believe there is a CircuitPython library for that DAC already. So let's go see if we can't just do this one. So it is in the CircuitPython library bundle, which I probably have somewhere, but yeah, well, I know I have it. Should be under Adafruit. CircuitPython 9. Bundle. Lib. So let's see if it's, so what am I looking for? I'm looking for a 805241, right? No. I'm looking for a MCP 4725. Which is right here. That is a great sign. So we'll go and we'll throw that into our That's funny. That's funny. It wasn't even powered and the signal was getting through. That's suspicious. All right. So we'll copy this. So then we'll be able to use this. We'll be able to use that in our Python code. Oh, yeah, okay, it's still working. Huh. It is a little bit low on the voltage, though. It's only going to about 2 volts. Wonder why. That was a lot of work to get RDP working. I might actually know why. If I take this out, and what if I plug this in instead? No. Okay. Well, anyway. So this is what I'm seeing. I'm not sure why it's only outputting to about 2 volts and not all the way down to 0. So we'll have to look into this a little bit closer. I'm not sure what that's about. Okay. Now, what I want to do is go and play with the, let's see, is there an example? Oh, come on. I have to go back to something else to look at the examples. So examples, let's go max 47. Oh, good. MCP. There's this example. Simple test. All right. So we're going to put this over here. Put this one over here. Oh, I know we're going to do 2. We're going to file save as scan.py. And we're going to do another file save as code.py. Yep, replace it. I'm going to take all this. We're going to do all this. And basically, we're just going to be like, all right, what do we got going on here? This is just going to start changing the value. Okay. Let's see if CircuitPython is complaining. So, in value, no I2C device of 62. Oh, is there a way to tell it my address? Because my address is not 62. Really? Really? It's hard. It's hard coded as 62. Ah. Okay. So that should be changing its voltage. So let's see if that's having any effect on here. Oh, so div, that's why. Div is a voltage divider. That's interesting. I guess I could have RTFM'd, huh? Yeah, okay, so that's what's going on. That seems like a terrible use of a DAC. So what we got to figure out is what is the voltage to make it big. So let's just do this. DAC value raw equals 4095 while 1. Oh, that's going to error out. Oh, that is the wrong code. What, did I close the other one? No. All right, so we're just going to come down here. We're going to say, don't worry about this. You know what it could have done. We'll just do this. We'll just say while true, DAC.raw value is equal to 4095. Okay. And now we're going to make it 0. Okay. Boy, this really feels like I don't need to have a DAC here. What if I made it 1024? Yeah. I wonder why I thought that was going to make sense. Okay, so we're just going to delete all these comments because none of this, I care about none of these things. All right. Now the significantly harder part comes because I don't know how to write I2C instructions yet on CircuitPython. But we're going to base this on, because now I want to play with the digital pot. And basically, this is a Python example of how to talk to this same digital pot over SM bus, which we don't have here. But I think all I care is to do this and this, which actually I think all I really, really care is this. And then the rest of this is, who cares what it does? Followed for the wrong code. Thanks for the follow. Welcome, Captain. Hello, Frackery. Welcome to the stream. Okay, so now what we got to figure out is a CircuitPython write I2C raw, I2C write example. This article looks promising. So, right, I know how to, wiring it up is not what I'm worried about. So we get our I2C bus, we've got that. Yeah, that's fine. But now I want, I want to know how to do a raw, I want to know how to do raw reads and writes through CircuitPython. So is it write 2? So the bus io.I2C write 2 is the start of transaction, the address, the list to write. Okay. So I think all I want to do now is writing to 805241. So I want a I2C write to 0x2c 000x80. All right, let's see if we get an error. Function requires a lock. No, it doesn't. You're a lock. How do you do a lock? To lock the I2C bus, you want to use a special loop that waits for try lock function to succeed. No. Okay. Why does it need a lock? Let's see. Before you can make calls against I2C, you first have to take control or lock it to ensure your code has exclusive rights. There's a few ways. So, oh, I see what they're saying. So we can do this, and until we get a lock, print waiting for I2C. We'll just do this, and then we'll write, and then we will do I2C dot unlock. All right, let's see what happens now. Extra positional arguments given. You're an extra positional argument. I didn't follow the write to. Yeah, okay. I should have done bytes, and then it'd be this one, this one. All right. Invalid syntax. You're an invalid syntax. Okay, so it wrote, I don't know what it wrote, but it wrote something. See this, okay, here's the problem, is I need now to be able to see the clock. How I can do that? I guess I could actually close this one for now. I don't need this project open. Then we can go back to the old one. Because the circuit we're looking at is the same between the two. I guess I had the new one open because if I wanted to make changes, we'd be able to. Okay, so our clock comes in here, but it doesn't go to anything else that I can clip onto. Yeah, no. Nope. I don't know. I think I can get on that pin. I'm going to try. I think I can do it. So my goal is this pin right here on a TSOT 23. I'm going to try to clip to that because that's the only other place my input clock exists. I guess the other thing is I could clip to the bottom of the pin maybe. Or I could put a wire on it. Maybe I could put a wire on it. All right. Well, we're going to try this. Okay, so let's go ahead and disconnect that. Let's go back to here. And then ideally what I want is I want to know, I guess we'll try this first and just see if I can even do it. I don't know what I just lost. Oh, ground. And I don't care about this one. You know, I'm going to try it on this board just because I have leverage on this one. I just want to see if this will even clip to the super teeny tiny pin that I'm trying to clip to. Maybe this board, since it has the chip I need. I think I can get it on there. Because I've had so much luck with these tonight, I just can't imagine that it's going to be a problem. Really? It really isn't the right size. Come on. We're going to try. We're going to try. We're going to try. And then I just bent this up, so that's not going to work as well. Nope. Okay. Nope. I don't like how finicky this is going to end up being. So I think a wire on the pin is going to be our best option. I should have made this a test point. Well, I guess I sort of did, but I didn't expect to have to be able to clip to it. Because the pad right next to what I'm trying to clip to is the same signal. Or, man, I wonder if this is going to work well enough. Nope. All right, here's my next other thought. Okay. Okay, I know what we'll do. I don't like this, but I don't have a better option. We'll just come into the breadboard and let's go like this many. So we'll say this is the signal will come into here. I will connect this scope into here. And then let's see, this doesn't get connected anywhere. I need to get this out of here. We'll go ahead and reconnect this ground somewhere. This will be fine. This is actually a good place for it. Okay, and then I need another jumper wire so that we can jump to, yeah, because I jump over there. I should have just brought the whole thing over, shouldn't I? I don't know why I was thinking earlier I wouldn't need another jumper. Okay, now we can see what happens when we go from this one to this one. So the idea is generator comes from off screen. Oh wait, so generator comes from here into here, and then it goes back into channel 2 of the scope, so we can see channels 1 and 2 on the scope next to each other, because channel 1 is the output of the clock delayer, and then that goes in. So that might work. Let us find out. All right, let's come back to here. It's like, okay, that's fine. And then we want to restart connection. That's fine. Reload. The code is running. All right. Okay. So right now, they are on top of each other. Or roughly, pretty close. The fact that this isn't coming down to 0 though, so the orange is the out of the clock generator, that bugs me. But maybe that's how it normally works. That's bothering me. Okay, so now what we can do with our code is let's find out if changing the potentiometer does anything. So what we could do is in range, how do you do a range? Is it something like this? Time.sleep 200 100. Okay, line 20. Yeah, I never remember how to do for loops in Python. Oh, okay. '21 invalid syntax. Really? Because would it let me do a 128? Oh. Like, is there like a hex conversion? Ah. Oh, Python. Okay. So now it should be writing values like really big. Oh. Oh, wait a minute. 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 What? Oh, this just caused it to go crazy. Let's change our trigger to channel 2 since that's actually our clock now. Well, that isn't at all what I was expecting to see. Am I on this one? What is this one supposed to be? Command 080, or 80 is the input resistance. So that is the resistance value. Okay. Oh my gosh. Oh. Oh, look at this. Look at this. It's actually doing it. It's doing it. It's doing it. Man, that signal integrity is terrible. I've done something wrong. But it is literally, it is, as the code loops, it's delaying. So this is, the blue is the input, orange is the output, and it's getting delayed as expected. But why does this look terrible? I wonder. I wonder if the chip's not soldered on correctly, if it's damaged, or if something else is going on. Because it's also a jittery AF. And why does it have a shelf? Also, huh. Okay. I just remembered there's something about one of the input signals that qualifies it on the rising or falling edge. So that's important. What is the maximum input voltage for this thing? 6 volts. Okay. I was just wondering if maybe I'm blowing something up. Yeah, it should run between 2 and 5. Okay. See, I'm looking for a tape. Wait. I wanted to look at this real quick. Yeah, so figuring these codes out is going to be a nightmare. See, that's what I thought. I thought the N divider changed the time and not the supply voltage. This line right here bothers me. If the voltage generated by the output of a DAC, it must track the V plus supply. So I wonder if I have if I have them turning on in the wrong order. Okay, I want to try. I'm just messing around now. So yeah, it's got a really weird wave shape. I'm not sure what's going on, but by changing the div, this is like much farther down now. The other thing is look how jittery it's getting way out here, wherever it's at the moment. What I really need at this point is I wish I had soldered to the other I2C pins, because I would actually like to plug the analog discovery in and see what the command is. I mean, I guess I could print it out, but So I'm going to do this again, but I do 256 because I just want to see what's going on. Is that maybe, the other thought is maybe that's why it seemed like its output was only half yeah, that's what happened. When the div signal was at 0 volts, it seemed like the output was like only halfway because it's doing this funky thing where it's not going to 0. It has this new low level that seems to vary with the value of div. Oops. Must have hit Control C at some point. So let's go to 4095. I want to see what that does. Oops. What? Okay. Well, that's not doing anything useful. Let's just go down to 2000. I think, hey Flask, I think I have some reading to do in my near future because this is not doing anything like I expected it to do. Other than when we change the value of the potentiometer, the amount of delay does change. Now, the problem is none of this stuff is linear, like none of it. So there's the div code, which is determined by the potentiometer, and then there's the polarity of that div code, which will determine whether I think it's falling or rising edge, and then the value of the end divider is you take the voltage and then you figure out what the voltage would be, I think, and that's what the divide ratio is. And then that's how you end up with the certain range. I mean, I'm actually really glad I finally got this working because now I can start to think about how this chip actually works. Okay. I don't know. I do know one thing I want to try is I want to try hitting it with my soldering iron real quick and just make sure we've got good solder joints because I had a lot of trouble with this setup. I just had a brief thought. Okay, that's not why. All right, so let's come over here. Nope, 350, turn this on. What I was thinking is the digital discovery was running the clock signal in all the time. And I was wondering if that was causing me trouble. Yeah, actually, let me hit this with a soldering iron. And then I will explain what the circuit is, because I don't think I've explained that for a while. It helps if I turn it on. I was like, man, there's like no smoke from this at all? Are you kidding me? So what we've got is, we've got a chip that delays clocks. And it does it based on 2 analog voltages on 2 of its pins. So one of the pins, I have a digital to analog converter for some reason. And on the other pin, I have a digital potentiometer for some reason. And I frankly, I don't remember why. And so at the moment, I'm just kind of giving it DAC and pot codes. And I'm not entirely sure what it's doing. But the funkiness of this signal has me concerned because it should be a clean output. at the very least, it should be going from 0 to VCC. I don't know why it's not going all the way down to 0. So that's why I had the idea, let me hit it with a soldering iron and just see if I had bad solder joints. So, and then just to show, this is, in short, this is the circuit we've got going on. So this LTC 6994, that's the delay circuit. Clock signal comes in, clock signal goes out, and it should have a delay based on the values of set and div. And so then I've got a couple of chips out here to try to control those voltages, because the idea was for the state mode logic analyzer, I wanted to be able to program a certain amount of delay, or at least give steps of delay of the clock. All right, so then let's, nope, that doesn't change it at all. All right. So that's why I say at this point, I think I have some reading to do, because I need to figure out, I must be doing something wrong, or I've got a problem with this IC. I don't think it has anything to do with the breadboard, but I am certainly willing to accept that it could be a solder related issue. I do have another board, but it doesn't have headers on it. So I guess I could throw headers on it real quick and see if it behaves the same. You know what? Why don't we do that? Just to rule the solder issue. Either it'll act the same, in which case it doesn't matter, or it'll act different, in which case that will be better. And I think that will be a good, I think that's a good test. So let's go ahead and wire up this other board. I also wonder if what else is that signal connected to? Okay, it shouldn't be. It should be an input going into the RP2040, but I just realized maybe there's an issue there. Okay. Regardless, I want to let's architect up the other board. Architect, not architect. What's the word? I forgot. Okay. So first up, let's get the 2x2. This one looks good to me. And in fact, you know what? This time I am going to put headers on both of the I2Cs, since it only take a second, because I would really like to have access to all of them. I really, really want to be able to look at a decode on the I2C so we can see what values are getting written. Although if this works out a little bit better, it may not matter. Hold, come on, hold. All right. 1, 2, 3, 4, 5, 6, 7, 8. Don't need anywhere near that many, but it's just easier to do it when there's that many. Frankenstein, maybe? I mean, this whole project was a Frankenstein project, and so I should back up a little bit. So what I'm doing, so this was the first revision of this project, which was a nightmare for lots of reasons. And ultimately what I realized is originally I was going to use an RP2040, but the problem is they just don't have enough IO pins. And so at some point I just said, you know what, to heck with it, it's just not going to work out. Then when the 2350 came out, I was like, hey, there are now enough I/O pins to do the things I want it to do and implement it in a way that's better than I was originally going. And so now I have a renewed interest in making this work. However, I never got this circuit. I never played with this circuit. So I wanted to spend a little bit of time to see if my clock delay is going to work the way I wanted it to before I put a bunch of effort into reusing it in the 2350 version of this project. Because I think the 2350 is going to be like my gateway to an FPGA project. So basically, I'm going to prototype this whole thing with the RP20 or 2350, get all the basic functionality I want, and then I'm going to step back and say, okay, how do I do this in HDL? Because really, for what I'm trying to do, a logic analyzer would be so much better. Or not logic analyzer, FPGA. But that's a pretty big step function. Okay, that's really good. I'm glad with that. I'm happy with that. All right. So we got both of those done. I should have just put a big header on this other one, but whatever. All right, so what else did we need? We need to get signals on the clock in. So let's get a couple of pins for that. These look like they'll work. All right. Yes. Cool. There we go. All right. And then let's see, what else do we got? So I'll be able to get access to the clock here. You know what? If I can fit this one, I'm just going to put it down anyway. And then that way I don't have to futz with anything. It's already available. Okay. All right. So what else did we add connect signals to? So I had to do that one, and that one. All right, so we've got all the same signals now. Cool. What are you running on the 2350 Linux? No. So right now, we are doing this with, well, right now I'm using CircuitPython, although I'm doing it from ESP32. But the 2350 is just going to run the C SDK. It won't need an operating system. I mean, almost all of the work is going to be done in the PIOs. Okay, so, and the Linux implementation for, actually somebody did get Linux running on the 2350, even though it doesn't have a memory manager. They are M33s though, so I think they're M33s. Should be this one back here. And then this will connect to SDAs on the outside. I think that's where SDA is at. Yep. And SCL is on the inside. We're going to change the color of that one, since I brought my other ones over here. All right. And then let's see, this is, yep, we're going to change that color because that's asking for trouble. I think this is our 5 volts, so that can go into here. Oh, nice. And then this is ground, and that can go pretty much anywhere. Okay. All right. So that should be the same setup we just had. All right. Let's go check that out. Yeah, the RP20, the 2350 is an upgrade to the 2040. So it's a dual core M33 ARM. It's a dual core ARM M33. So slightly more powerful than the M0. It also has 2 RISC cores that you can select, so that you can select between the ARM cores or the RISC cores at boot, but you can't have both of them. Well, you can have one of each, or you can have one of each running, but you can't have more than 2 cores total. So let's run this. Wow, this one's acting completely different. I2C failed. Interesting. Okay, did I get my signals swapped? So SDA is on the outside. SDA and SCL. Uh-oh, uh-oh. Darn it, this one may not work. Yeah, it's not seeing the shoot. It's not seeing the bus. Oh, I'm an idiot. Okay. Well, yeah, so this one's not working the same way, is it? Well, the good news is it's at 0 volts, which we weren't getting to be. Oh, there's a minor issue here. Well, that's interesting. There's a couple of codes where it does something, and then there's a couple where it does nothing. I'm going to put this back to 0 and see what happens. Okay, so this board is working completely different than the other one. First of all, the output looks much better, but it is doing what it's supposed to do. So there's definitely something wrong with that other board. But look at that. So basically what's going on right now is I'm going through the digital analog converter, and I'm just incrementing its resistance value, or basically moving the digital wiper. And so that's causing the clock divider, or the clock delay chip, to change the delay. So blue is the input signal and orange is the output signal. Ow. Yeah, let's pick that up right now. Well, I'm glad we did this, because this is definitely working much better than the other board. I don't know what it means yet, but it's better. So then let's put this to 256 and watch what happens. Interesting. I gotta think about how I want to do this now. Like, Like what I could do is write some code, because like I'd like to have something go through and automatically measure. Does this have a let's see, how about a it doesn't have a delay measurement. Darn it. Darn it, darn it, darn it. I mean, I guess I could use my real scope. I just can't believe this doesn't have a delay measurement to tell you the delay between the two channels. So right now, it's delaying 20 microseconds. Okay. So now let's do go back to 0 and just see if it delays the same amount. Looks like it's going to get to the same point. I guess the other thing I could do is what if we just leave it at, what if we just keep writing the maximum value and change the DAC value and see what it does. So let me do a save as. They don't have a save copy, do they? All right, we'll just do save as code, kinda working. And then I'm going to do a file save as. When I say they, I mean Sublime Text. Okay. So what I want to change now is I want to write change this. So we want to write this value I'll go ahead and sleep for whatever, 100 milliseconds, unlock it, and then for value in range 496, DAC is equal to, raw value is value, and then time dot sleep for 50 milliseconds. And then let's see, is that actually running? No. Line 23, oh. Line 23, why is that not happy with? Oh, I did it again. Stupid colons. Yeah, so changing that DAC value is not having an effect at all. Oh, there it is. Ooh. So I wonder what value, shoot, I should have been printing the values. I'll bet I know what it is though. Oh, did it jump again or did it go back? Wait a minute. Yeah, this is where having I2C decode would be really helpful. I wonder if it's worth setting up. let's go in here. Let's add logic. Wait, can you add logic to the scope view? Like, I thought you could. I guess not. All right. Some logic, what I want to add are I squared C, and it's going to be on, let's see, clock is going to be on, is it on the outside again? This is on the inside. So clock is going to be 7. Data is going to be 15. And let's trigger on I squared C. Start's probably going to be fine. Okay. So here we can see the payload increasing. All right. Now, how do I get this to be on the scope screen? Go away. What are you doing? Okay. I thought there was a way I could force... I thought there was a way to actually get the digital lines on the scope screen. There it is. Okay. All right. Actually, so we can... Okay, so that's what it is. So I want to close this one. Click I squared C 7 and 15. Okay, and then we can run the scope, which should also run that at the same time. Then over here, we're going to rerun the code. But then we've lost our scope traces. Why? Huh. That's weird. I don't understand why the scope traces... Wait a minute. Why are these offset to 2.3 somethings? Okay. Let's do channel 2. Hey, Viper. I feel like I broke something, but I don't know what. So let's kill that. Oh. Oh my gosh, I know what I did. So dumb. I stopped running the pattern generator. Okay, so then what we're going to do is say trigger on digital, and on here we should have the start of a packet, which is just a mess at the moment. And up here, if we do trigger on an edge, then we miss the packet. Like right now, okay, but if I see, I guess I could use this though, because if I look at this, I can at least say, okay, so somewhere around B3 is when it resets. See, I'm not going to be able, then I got to do it up here. Or, what if I said normal on digital? Nope. It's because they're not phased align. That's bummer. Anyway, so, okay, so just to back up, let me explain what's going on, because there's a lot of things on the screen right now. So this is waveforms. I'm connected to a analog discovery 2. The blue channel is the output of our, the blue channel is the input of our circuit. It's actually the pattern generator that's down here. The orange channel is the output of our circuit, which I'll show you the circuit in just a minute. And then the stuff down here underneath the digital waveforms, this is the I2C decode, so that we can actually see what I2C messages are going across the bus, because these are going to a couple of chips that control the output of this signal. And so the circuit is this. It is a LTC6994, which is a clock delay circuit. And based on the voltages at div and set, it changes the amount that the signal gets delayed through this chip. And so there's a digital potentiometer, which is controlling the voltage at the set point. And then there's a DAC to control the divider ratio. So basically the way it's supposed to work is this chip has a certain range at which it can delay signals. And then by changing the value on divider, you can expand those ranges. And so what I was trying to do is figure out what those magic numbers were automatically, but this isn't working out. So what we're going to do is I'm just going to come back to, is this the only window I have open? We're going to come back to here. I'm going to call this bad code. We're going to go back to kind of working. And I'm just going to make some educated guesses. Oh, wait. This should just be code. All right. So now we'll go back up here to channel 2. I'm going to expand this out. And what we know is we don't need a loop. I don't want a loop for the moment. Instead, what I want to do is I just want to write 255. And then let's do a print so that we can see what's going on here. Print writing to MCP 4725. All right, so I'm going to try 128. Make sure code runs. The code ran. So right now we're getting a delay of 20 microseconds, roughly. So the blue signal is the input, orange is the output. And then if I change this to 129, actually maybe what I could do, let's think. Maybe what I should do is put this like here. And then we'll have this over here. And then let's bring this right to here. And then let's go to preferences, appearance. That's basically where I am, but it should be okay. Let's make this like 14-point bold so that it's a little more readable. And then we'll just make this come down to about here. Okay. So then I'm going to hit Control D to make sure that that code ran. We can bring this over here. All right. I should have done this a long time ago. Okay, so 129 didn't do anything. Let's try 256. So I'm trying to figure out what value that we write to the DAC that causes us to go to the next range. Okay, so 512 might be it. Let's add another delta cursor or marker or whatever they call them. So that one went to, let's see what's going on here. I actually think I'm going to close that for now. And this I'm going to try and put into the same window because I just need to know that it's running. And that way we have more stuff we can see. Okay, so that jumped to 156 microseconds. Okay. And then let's do 1024. And then 1024 we lose the signal altogether, which I think is the case for anything above 1024. Okay, so 10 what's after 1024? What's like plus 128? Okay. Interesting. What about 768? I'm going to change this to value is equal to 760. Go back to 512 because I'm let's write that out, and then that way we know for sure when we look down here we're seeing what I think we're seeing. Okay, so something is definitely wrong because now it's not responding to values that I know should work. So 256, I thought 512 was our upper limit before. Or 512 is just having no effect. Oh, I see. And then if I come back to 512, it doesn't like that, but it likes 256. What about 511? Huh. So we only get two ranges. I'm not sure why. Is that to 256 and 511, or is it 255? Huh. I'm just trying to find where does it switch between this range and this range. This is weird. Because now it's not jumping back over again. So there's something else going on. I don't understand this behavior. Or 256 is not the crossover point. All right, so 384. What if I put in, so let's go back to 128. And what if I do 300? So it's not 384. Uh-huh. Okay. So if I go 128 to 256, will it jump? No. All right, 260. 265. All right, 128. 265. 270. Yeah, this is feeling like a very much a hysteresis issue. So 280 got it to swing back. Okay, so I'm going to go to 128 again. I'm going to go to 280. Huh. So it's like 128, 280, and somewhere around 511 are all magic numbers. Which these two are probably not the actual magic number, or none of these are, but there's something about those 3 voltage points that messes with this thing, but I'm not sure what it is yet. Okay, so let's leave it at 280, and now I want to go back to running in the loop. Yeah, because like in this range, this almost seems like a fine range to be in because we still get 250 steps, but we're only getting 150 microseconds of delay, which is, well, okay. That's actually quite a bit, I guess. I was thinking nanoseconds. Okay. Oh, hey, Ito. Yeah, you just made a really good point. Okay. Yeah. So Ito's question is, are we really losing the signal above 512 or whatever? Or is it delayed so much that the input clock is too fast to see it? Yeah, okay. I see where you guys are going. So let's do this. Let's go change our clock speed for now. Let's just make it 100 hertz. So was that 10 times slower? So now we've got plenty of clock pulse time. Okay. Yeah, I see where you guys are going. Let's see how this works out now. I'm gonna get rid of the loop because all I care is the maximum value. And then, so let's do that. Make sure we still get the same thing again. So we haven't changed. So now if I go to 5, I'm going to put 512. Yeah, that wasn't the magic number. All right, so let's go 600. There's a magic number in here somewhere. I just don't know where it's at. Okay, there's 600. Okay, yeah, you guys are right. That makes sense. So, yeah, because then let's just go to 2000. And that's way too far. About 1000. Okay, let's come back to 600. Oh, I wonder if it's literally, if it's half a clock period is its maximum that it can handle. I don't know how it knows what the clock period is, but it feels like that's where we're getting to about half of the clock period, and then that's as much as we can get out of it. Or maybe that's a quarter. I mean, the thing is, this chip has no idea when the falling edge is coming, right? It only knows it saw rising edge and then it delays for a while. But frankly, I need to spend some time with the data sheet and understand what's actually going on here, because I don't know what this relationship necessarily is. Can I write a larger value here? think so. Okay. I need to double check what the commands are. Was this 0, 0, right? Yeah, this was 0, 0. Ah, interesting. Might be exponential. Yeah, I don't know what the actual mathematical relationship is. It's not linear. So the div code is what we're setting with the DAC. No, the div code is what we're setting with the, no. In div is what we're setting with the DAC. R1 and 2 are what we're setting with the digital potentiometer. Let me double check that. Make sure I'm okay. Nope. I'm glad I looked at this. Now I remember now. Okay. This doesn't show the other signal. Yeah, maybe this is the set right here. Okay, so the potentiometer that we're playing with is, or the DAC. Shit, I gotta look at the schematic. I've got myself completely confused now. This chip seems so promising if I could just understand how to use it. Okay, so div comes from a DAC. And set, which I think is actually iset, comes from this potentiometer. And so when we look at this diagram, when they talk about R1 and 2, they're actually talking about a voltage divider for the divider. So in div. And so there's some relationship. It's something like this. It's this, I think this is there's some relationship like this that relates to what value is here. And so that's how our divider gets set. So there's something going on there. I don't fully understand it. That's what's happening there. The iset, where... See, our R set is the only thing I have control over. So I think if maybe it's down here. So R set is this divided by this. So if I have this set to a certain resistance value, I can calculate what the delay should be. I don't know why I did it this way. Yeah, actually, this is not too far from what I try to do. I don't know why they have this in here. Oh, for that one. Yeah. Div comes from a DAC. If aliens are listening, do they think that's baby talk? I think if real people hear some of this stuff, they think it's gibberish talk or baby talk or whatever. Okay. I think at this point, I've established what I wanted to establish. I didn't want to open that. By changing the two voltages on these two pins, I can create a delay for the clock. That was the goal. Now, whether I understand how it's working, that's a completely different story. But at least I also have a board where I can play with this circuit more. Because that was sort of where I was going, is I wanted to play around with this circuit to try to understand it. And so at least now I've got something we can work with. to try to figure out what's going on. Yeah. Okay, I got one more thing I want to try. So because like what I wanted to be able to do at this point is now I want to like put those equations into a spreadsheet and try to calculate what I expect the changes to be and try to make a correlation between whatever values I put into the DAX are what I expect them to be. Because right now I'm just kind of throwing numbers and seeing what happens, and I'm not not really following it. So I want to do at 0, and I wanted to see so that at 0 volts for the DAC for div, I get a delay of up to 20 microseconds. And then I wanted to change this to 1 and see what that makes our delay. And we get a delay of 200 nanoseconds. Ooh, I was really hoping for a little more resolution than that. Okay, so then the next thing I want to try is I'm going to go into patterns and I'm going to run this to a megahertz and see if it still works. Oh, that's not what I meant to do. Oh, that's interesting. Yeah, we're only getting about 150 nanoseconds. I was really hoping for tens of nanoseconds. Hey, Silent. I'm glad you did a mountain bike ride. 33 seconds? Yeah, it'd be a heck of a delay. I did do a loop where I increment it and decrement it. The problem is I don't have a good way to correlate what it's changing to and what's happening on the screen at the same time. I guess we could print it out and just go really slow. But yeah, that's what I sort of was doing that earlier, but it wasn't. The bigger thing is, yeah, that's probably what I need to do and just go slow. I was trying to figure out a more efficient way, which was less efficient. Yeah, no, that's fine. That's a valid approach. It's probably what I should have been doing. This is also making me think I might want to put the output of this clock divider through a Schmidt trigger, which will then add another delay, because it's not the cleanest looking output. Anyway, so then let's go 0 on here. What does 0 do? Yeah, so 0 is actually a slightly longer delay than 1. Nice. 2 is longer than 0. 3 is half a clock at 1 megahertz, which is okay. Okay, that's actually more resolution than I was hoping for. I'm still not sure why 0 is. Anyway. Okay, one more test. I think this can go to 10 megahertz. Okay, so that's our, yeah, a couple megahertz is going to be our limit. Let's try 6. Nope. Let's try 2. Yeah, okay. That's... I'm not sure how I feel about that. It was even at 2 megahertz. Yeah. Unless I can figure out a different divide. What's this table look like? Maybe let's just look at these numbers. Maybe I'm just not. Yeah, okay. This is basically saying it's only going to give us steps from 1 to 16 microseconds. I might have completely failed by not paying attention to the data sheet. A microsecond is just not enough. I thought I could do nanoseconds though. I thought that's why I picked it. Or you know what I probably did? I probably was thinking nanoseconds when I was reading microseconds. Shoot. Yeah, this just isn't going to do it. Because the idea is I want to be able to capture things on, say, like a 100 megahertz clock, and I need to be able to move the clock over like tens of nanoseconds to maybe 200 nanoseconds, which we're getting one click over, but this chip is like $10, and so for that one click, I'm paying an awful lot. And then at 2 megahertz, the maximum speed we can put through this is 2 megahertz. Shoot. And just keep in mind, we're not trying to make a clock divider. We're trying to make a clock delay. And so, like, I feel like I'd almost be better trying to set up some kind of timer circuit and just have a programmable one shot. Yeah. Shoot. I know that's what I did. I looked at this and was like, oh, this is totally what I need. And I need nanoseconds, not farts. Yeah. I just gotta double check this math real quick because I think, yeah. It's really not. No, I think I don't know that this is going to be easy to do in the PIO. Because again, we're not dividing the clock, we're delaying it. So I guess we could use one of the PIOs to detect the edge transition and then decrement one of the, I think there's a decrement command. Anyway. All right. Well, tell you what, this was fun. And I'm super glad that I played around with this board because it has shown that the circuit, let me rephrase, the circuit works, the circuit is working correctly. However, it is not working as expected because it's not going to do what I want to do. It is pretty cool though. Like to be able to do this is kind of neat. I mean that's cool. But if I had read the data sheet correctly, I'd realize this isn't going to work. I am so glad. You know what's funny is I placed a parts order today, and I almost bought some more of these because I know I only had enough to build the boards I had, and I'm so glad I didn't because, yeah. So, yeah. So maybe we will just do it in one of the PIOs. Shoot. Okay. Well, this was fun. On Tuesday, a new Atoms video came out. It featured this project, actually. This red board. It's called Bald Sense. If you've been here for a while, if you remember streams from back in the 2020, we made a revision of this board that was terrible. Macrofab sponsored a video. They built some of these boards for me, and they're working really, really well. In fact, I did this up this morning. I'll show this real quick. What is Adafruit's IO? Is it io.adafruit? Bald Engineer Dashboard. So I actually have a Bald Sense sitting outside. Oh, this doesn't. Oh, how do I get a longer trend? Oh, there it is. I want. Let's go 2 days. Now, why did that move? All right, let's do 2 days because I just. What the heck? What the heck is it doing? I want to like this service, but this web interface is just absolutely terrible. Like, I don't understand how they got this so bad. It's a heck of a lot better than what I would have made. But anyway, so yeah, so what I was trying to, so you can see how the temperature outside is. We had a really warm day yesterday, and then it cooled off, and and then we had some rain, and then it looks like, relative humidity is dropping with temperature. The lux level is kind of messed up because I changed where its position was, and so it's not getting as good of sunlight, so it just kind of sits kind of dark. But you get an idea of how long there's light outside. And then this is the thing I was really interested in, is how the battery's doing, which it looks like it's finally starting to taper off. So I should probably go grab it and measure the battery voltage and see where it's at. So, yeah. Assuming you know the clock frequency in advance, or at least how much delay you need, the PIO can work. Yeah, so the idea is you should know the nominal clock, but nothing you should do should depend on the clock. So I'm building a state mode logic analyzer, which means the DUT drives the acquisition of the samples. And so that's why, in terms of setting up a delay, sure, we should know what the nominal clock is, so we should know what the correct delay should be. But in terms of implementing the delay itself, it has no knowledge of when the next edge is coming. And so that's, in my mind, that's what's different between a divider and a delay. Because with a divider, you're sort of relying on the next clock to be you basically burn one clock so that you can start dividing, or you burn n+1 clocks so that you can divide out the rest later. With a delay circuit, you don't know when the next edge is coming. So whenever you see an edge, you have to asynchronously count and then recreate the clock. which is where I think Geek is going with the PAO. So I did not cover any of this interface in the add-ons video, but I covered the project itself. I'm planning to do a video that compares log files to Grafana to this to something like Goliath or Blues or some other like IoT cloud vendor. But I want to do a video where I compare, once you have IoT data, or if you have IoT data you want to put somewhere, what's examples of things you can do with it, at least in terms of viewing the data. Because like when I look at this stuff, I don't see these trends at all in the Excel file, in the CSV. Even though I can see the temperature, like I can look at it and say right now the temperature is 25 degrees, but I don't notice the trends. And maybe specifically for the batteries, because these are just basically random numbers to me. This is just the ADC readings. I didn't bother to calculate the voltage. So anyway, yeah. Yeah, so in the video, I used Grafana because I had a CSV file that I could just upload, and that was like good enough for the video. So yeah. All right. So yeah, actually the add-ons page, I didn't realize that you put the add-ons link. I forgot to put this over here. Yeah, the add-on, so I did a long write-up, and then there's a video and stuff. So anyway, I'll look at more stuff on that in the future. Basically, my goal with this Bald Sense project is to kind of start from an idea and then get to what would be a sellable product, what would be a sellable IoT product. I have no plans to actually sell it. I just feel like there's a lot to learn in between those two things, because, you know, in my mind, it was going to be like, oh, I just put these sensors on an ESP32 and then I'll use MQTT and everything will be easy. And I'm starting to realize there's a whole lot of in-between stuff that maybe I don't want to handle, you know? So anyway, so I put the link up for that. You see a Pi. There's the RP2040, but we actually didn't use that today at all. So there's an RP2040 on this board that we're not even using. We were only talking to this circuit. This board over here is an ESP32S3. I have a Pi Pico 2, but I haven't used it yet. So yeah, I don't know what I'm going to do with it. But yeah, so I do a lot with RP2040s. It was my favorite processor. Now it's probably going to be the 2350. So, all right, I'm done for tonight. Thanks for coming by, guys. For those on Twitch, let's go see real quick. Man, Sid is on, but I think he's been on for like the entire day. But he's doing Jamtown, so we'll just go raid him. And then yeah, so go check out the new add-ons video. There's also the Discord if you want to join Discord. What's the link? Something like that. So thanks for coming by. Remember, well, I hope you find time to do something that you enjoy doing. Or what do I say? No, remember, find time to do something that you enjoy doing. And if you do, please think about sharing it with other people. And I'll be back next week. Very likely we're going to work on something else next week, but we'll see. Yeah, especially now that part of the circuit's working. So, okay, guys, take care. Thanks a lot. Bye. Yeah, we're going to raid in just a minute.